Bismillahirrahmanirrahim. Assalamu alaikum viewers and welcome to my channel, and in today's video we'll try to understand the polynomial approximation of a function, and we'll try to understand how we extract Taylor series from the power series, and how Taylor series helps us in getting a polynomial that helps us to approximate a certain function, a function which is a non-polynomial in form. Okay, so what exactly we are going to deal today is that if we simply consider a function that can easily be differentiated n times on a certain interval I. Okay, we just consider any function, and this is a non-polynomial function. It could be a logarithmic function, could be exponential, it could be trigonometric, like that. So, and it is easily differentiable n times in any open interval I. Okay, so that's it. Now our goal is to find a polynomial function that can approximate f at a number c in its domain. So you see, I just say that let c belongs to this interval I, and I just say that if I evaluate this function f of c, I'm getting some answer. And then I say that how about if I just find out a certain polynomial, so that once when I replace the c, if I replace the variable of that polynomial by the c, I'm going to get the same answer once when I substitute c in this function. So it should be exactly equal to that polynomial, and I just represent that polynomial m of x, and I just say that it is c. So this is said to be a certain polynomial. So how we are going to obtain this polynomial, and how that polynomial looks like, that is going to behave as the best approximation for a certain function at a certain point that belongs to this interval, and this is the interval that contains infinite number of points, and at every point this function is differentiable n number of times. That's what it means. Okay, so now as far as the c is concerned, you see this is a new topic, and whenever we try to understand something new, we try to understand it in easy-going way. So if I just pick up a simplest case, and I just say that let c is equals to 0. Alright, and I just say that this is the special case of understanding the polynomial approximation of a certain function, and I just assume here for instance that let your f of x is exponential function e of x. Alright, this is it, and I'm going to resolve this function, and I'm going to obtain a polynomial that best explains this function at a certain point c equals to 0. Alright, so if I say that I'm going to get m of x polynomial such that this polynomial at this point should be exactly equal to your f of 0. Okay, so and here I know that my f of x is e of x, and I'm going to replace my x with my 0. I'm getting 1. So my m of 0 should be equals to 1 because f of 0 is 1. Alright, what is my m of x? This is the case. So, and that's what I am subjected to find out. So I just assume here that my m of x is equal to a0 plus a1x. Now a0 and a1 are any real numbers. I have to find out these values of a0 and a1, whatever they could be. And one thing more, that in order to understand, there are several ways of finding out the polynomial approximation. I'm just considering here a condition in order to understand, in order to evaluate, or in order to extract the best polynomial that shows best approximation of a certain function at a certain point c. So the condition that I am using here is that the slope of this polynomial, okay, that can easily be understood by means of the derivative. So the slope of this polynomial at a certain point c equals to 0 should be exactly equal to the slope of this original function at a certain point c equals to 0. Okay, so I just say that my m dash at 0 should be equals to my f0. Okay, now I will keep these two conditions in my mind before moving forward. Okay, this is the first helping tip, that my polynomial and my function both should passes through the same point. Okay, like if I say that, if I just try to plot here a graph, okay, and this is the, what you say, exponential graph, it looks like something like this. Okay, so at 0 it is coming at 1 point. Okay, and my polynomial over here, it is a linear polynomial, you can see, so it is going to give me a straight line. And straight line should also seems to be like this. This is your m of x. Okay, so you see this is my f of x. So you see at 0 my f of x is also giving y coordinate 1, and m of x at points x equals to 0 also giving me the y coordinate 1. So this is the case that I'm going to follow. Okay, so, and we are going to expand this polynomial with at this point 0. So in other words, you can also say that my polynomial is actually it is centered at 0. Okay, because we are discussing the special case c equals to 0. And another case, that the slope of this polynomial and this function f of x at a certain point c equals to 0, they should be same. Okay, this is the case. Now we move on and we try to find out what is going to be the value of my a0 and a1. So over here I can see that my m dash 0 and f dash 0 are same. So f of x is ex, and the derivative of my f of x is also ex. So this shows that my, if I put x as 0, so it is giving me 1. Alright, so this shows that f dash 0 is 1, so it means my m dash 0 is also 1. Okay, so if I differentiate this equation with respect to x, I should do over here, that if I differentiate this equation with respect to x, I'm getting simply, if I differentiate this with by means of this, so I'm having what? The derivative of a constant number is 0, and the derivative of this thing gives out to be a1. So I'm having simply a1 here. And once when I put my x equals to 0, then it is equals to my a1, and a1 is equal to 1 if I compare this equation and this equation. So here I come to know that my a1 value is equals to 1 here. Alright, this is it. And then I just keep on moving here. So here, if I pick up my mx, this equation, and I replace my x by my zeros, m of 0 is equals to a0 plus a1. At the place of x, I will put my 0 here. And I know that my m of 0 is equals to 1, so this thing is equals to 1. So I come to know that my a0 is equals to 1. So this reveals that my equation m of x comes out to be, and I just call it is containing only one variable. So this is my m1 polynomial, for example, and I just say that it is 1 plus 1x, or simply x. This is my first polynomial. And if I just try to analyze this polynomial by means of the with respect to this function, and I just try to analyze both these functions on a graphic calculator, I will see that up to how much extent they are giving me an overlapping region. Okay, they are giving me the straight line 1 plus x and the polynomial e of x, at how much far they are overlapped, or they are giving you a common overlapping or common ordinates, I must say. So if I just see here the graph of this m of x and f of x, what I get. So if I see my exponential graph, it is this. And once when I try to see the graph of your 1 plus x or m1x, and you can see one thing more, that at x equals to 0, this is the 0 point, and at x0 it is having y coordinate 1. Okay, we are talking about exponential. Now if we just talk about the m1x polynomial, which is 1 plus x, this is the case. This is the graph of your the linear polynomial, you can see. And you can see that at x0, this polynomial is also having y coordinate 1. And you can also notice that up to certain region, both sides at x equals to 0, here to here. Okay, so at the certain interval, it is very small interval, you can see these two graphs are overlapping. Okay, from here to here. So actually this much distance ahead from your 0 at the left side, and this much distance ahead from the 0 at the right side, you are having an overlapping form of these two graphs. So how about if I just increase the number of terms of my polynomial in order to see, obtain more common overlapping or more overlapping regions, in order to see a wider interval that can give you the best approximation, that is going to give you the polynomial and the function providing you the same y coordinates at certain values of x. So I need to increase those values of x. I need to increase the length of my interval in order to obtain the best approximation. So that I can do it, as far as I have understood, by increasing the number of terms. So let us try to see how the graph looks like of the polynomials if I increase its number of terms. So first of all, we'll just find out the number of terms, and then we try to analyze it through the graph. This was your first polynomial. Let's try to get the second polynomial, and I just say that let your m2x is equals to your a0 plus a1x plus a2x squared. This is a quadratic polynomial, and one term I have just added in this m1 polynomial. That's what I did. This was my m1 polynomial. Okay, I have just included one more term here, and I just call it m2. Now what I'm going to do, a0 and a1 are already available. I have to find out the value of my a2x squared. Okay, the second derivative should also exist in this interval I. Okay, because we have said that it should be the derivatives, the nth derivatives should exist within this interval I, where the value of c is present. Okay, so now what we do, if I just try to find out the derivative of this function, the derivative of this function is going to be 0 plus a1 plus 2a2x. Okay, this is the first derivative, alright? And this is the second derivative. The second derivative should also exist, and so forth. So this is, once when I differentiate this equation, I'm getting 2a2 here. Alright? Now, as your m2 0 should also be equal to your f of 0, your m2 dash 0 should be equal to your f of dash 0, and m2 double dash 0 should be equal to your f of double dash 0, and so on. So this shows that your m2 double dash 0 should be equal to f of double dash 0. This is the condition where your similarity, the condition that explains well the similarity of this polynomial and this function, the behavior, the similarity in the behaviors of these two functions. That's it. So as we know that if I just take another derivative of this f of dash x, where is my f of x? This is my f of dash x, right? If I further derivate this thing, I'm getting f double dash x, and it is also equals to e of x. So if I just replace it with my 0, it equals to 1. So f double dash 0 should be equal to your 1. It should be 1. Okay. So now f of double dash x is 2a2 and is equals to 1. So this thing explains that my a2 is equals to 1 upon 2. Alright, so this thing tells that my a0 is 1, my a1 is 1, my a2 is half. Okay, and also I can write this as my 1 upon 2 factorial, because 2 factorial is 2, so I can write 2 in terms of factorial as well. So now my m2x is equals to 1 plus x squared upon 2 factorial. This is my equation number 2. This is my second polynomial, alright? In the same way, if we just pick up one more polynomial, if I increase one more term here in terms of x cubed, and I just call that polynomial as my m3x. Okay, and it is represented by means of one more term, which is this. Now the first, the second, as well as third, the three derivatives of this polynomial should exist in this interval I. That's what it means. Okay, so I will find out all of my three derivatives one by one, and okay, following the conventional formula of derivative of xn. That's how I got. And now I'm going to derivate it second time. I'm going to differentiate this equation. Once again, I'm getting 2a2 plus 6a cubed x. Alright, now one more derivative I need, and it is equals to, therefore, 6a cubed. Okay, and you see the similarity in the behavior exists if all the derivatives of the polynomial should give you the same answer to what I get, the derivative of this original function f of x. Okay, so here my f triple dash is also going to be 1, but I should write it over here that my f double dash x was also equals to my e of x, as I did over here. I further differentiate this function with respect to x. Once again, I'm going to get triple dash of x, and it is also exponential of x. And once when I replace my x with my 0, I'm getting 1. So the third derivative of my m3 polynomial, m3 of x, is also equals to 1, and m3 of x is equals to 6a3 here is equals to 1. That's what I have followed over here. So this thing shows that my a3 is equals to 1 upon 6, and 1 upon 6 can be written as 1 upon 3 factorial. Okay, so this thing shows that my third polynomial can be expressed as 1 upon x plus x squared upon 2 factorial plus x cubed upon 3 factorial, and this is my third polynomial. And the same way, if we just generalize, we come to know that our fourth polynomial is 1 plus x squared upon 2 factorial plus x cubed upon 3 factorial plus x power 4 upon 4 factorial, and so on. You keep on moving till you get the mth polynomial, and nth polynomial can be written like this. It's nothing but the beautiful generalization, xn upon n polynomial, n factorial. So you see, once when you keep on increasing the number of terms, the approximation become more and more strong. Okay, the polynomial approximation of a function f of x becomes more and more strong. So let us try to see here on the graph paper. Not a graph paper, it's a graphic calculator. This was your m1x, okay, and this was showing you approximation from here to here, and that's it. So if I just put my second polynomial m2x, you see, and let me just remove the first polynomial because it's going to mess up too much. So it is showing the approximation from here to here. Okay, so you can see the interval has now enhanced. The interval which is showing x and y coordinates same for f of x and m of x, it has been increased. Okay, so let me remove this m2x. Let me introduce m3 of x with one more term addition in the polynomial. You see, it is starting from here. The similarity, the approximation is very well explained from here up to, oh my god, here. So you see the interval has further increased. Okay, whatever the x, y points are here on f of x, the same x, y points are here on your m of x if you increase the number of terms. So introduce one more, m4x. This is your m4. Okay, it is moving like this. Okay. So this much region up to here, if I further increase my, if I change my the range of my x and y coordinates, x and y axes, so it is going to be further, it is going to show you further further overlapping part. But I think this much is still quite good enough in understanding the concept that it is starting from here, the overlapping region going here, so it is further increased. Let's see m5 polynomial. Oh my, it's starting from here and then overlapping entirely on this exponential function. It is overlapping from this point up to this point. Okay, so you see the polynomial is centered at 0 and is further expanded. The interval is expanded at 0. Okay, so this point x at c is equals to 0, the interval is expanded, and the expanded interval is so obtained by increasing the number of terms of the polynomial, and it explains you the best approximation. So that's what the expanded interval is explaining, and the expanded interval is so obtained by increasing the number of terms of the polynomial. So that's what exactly we are willing to understand. Okay, how we are going to obtain the polynomial approximation. So you see, this nth degree polynomial approximation for the function f of x at x equals to 0 is called the nth degree Maclaurin polynomial for f. Okay, and if we repeat the steps for x equals to some non-zero value, I just call it c, for example. If we just try to repeat the same process for x equals to c instead of x equals to 0, then in that case the subjective polynomial is said to be the nth degree Taylor polynomial that explains the approximation for f, and we just represent it by means of, we just represent it in this way. And we are going to further understand how this thing has been obtained with the help of the power series right after this. But I think I should write down here first how the Taylor series or how the Taylor polynomial looks like. And this thing is obtained once when you try to expand your polynomial at x equals to some non-zero value. Okay, and you keep on moving till you get x minus c power n on n factorial e of c. But this is what you call Taylor polynomial. Okay, now as far as how we try to understand the Taylor series with the help of the power series, so over here we are having a certain theorem. We know that the power series, the function is expressed here, is expressed in terms of power series having this general form. So you see, we were having best accuracy or best approximation once when we obtain the n terms of a polynomial for a certain function f. Okay, but we will now approximate a function f by an infinite series. So a function f is said to be represented by the power series, which is this, okay, for all x belonging to some interval I. So over here, two concepts come in our mind that deals with the existence of the power series and the uniqueness of the power series. Like if I say that what are those conditions that a given function is going to have a power series representation, and what are those conditions? And in case of uniqueness, the question comes in our mind that when f can be represented by a power series, is there only one form, or is there only one kind of series, or is there more than one kind of series that can be expressed in terms of the power series, or that a function can be represented in terms of power series of more than one form, or is there just one type? So in order to understand the uniqueness, we are having a uniqueness theorem here, the uniqueness theorem for power series representation, that if you're having a certain function that can be represented by a power series, an infinite power series, this, where your x minus c, the certain number that belongs to this interval, an open interval, where r is actually the errors, and we are going to understand errors later on. Okay, so just understand these are the two real numbers, and your x minus c number belongs to this open interval. All right, so uniqueness theorem says that the coefficients a subscript k, they are expressed by means of this representation, or the derivative of your certain function f of x at point c. The coefficient is expressed in this way for all k belongs to 0, 1, 2, 3, and so on up to infinity, natural numbers. Now over here, in case of understanding the proof of the uniqueness theorem, I have just tried to open up this infinite power series starting from k0 to onwards. So I've just tried to open it up like this. Wherever I'm having my k, I'm going to replace it by 0, 1, 2, 3 consecutively, and that's what I got. Okay, and it is going infinitely. So I just call this equation as my equation number 1, because here you see as far as this x minus c power 0 is here. Whenever we are having power 0 on any base, it always gives me 1, so that's why I'm now having simply a naught here, and the remaining terms are written as it is. This is my equation number 1. I have to keep this thing in mind. So let's move on to the next step. Now in equation number 1, I'm going to replace my x with c. C belongs to your open interval I. Okay, where your derivatives where your function f can be differentiated infinite times at this point c. So over here, this is my equation number 1 that was written at the back. Wherever I'm having my x, I will replace it with my c, and that's how I got. So these terms, all the terms other than this one, will become 0. so they are vanished. So my f of c is equals to a naught. All right. In the same way, now I'm going to differentiate my same equation number 1 by means of my x at both sides. This is my equation number 1. So I'm going to differentiate both sides with respect to x. So what I'm going to get here, this becomes my f dash x. Derivative of your constant number is 0. The derivative of x minus c gives me nothing but 1. So it gives me simply a1 here. Now I'm going to differentiate this x minus c square, keeping this a2 out, and I'm going to apply here the formula of my derivative of xn, just this. Let me write it again. And over here we are going to apply the chain rule on the base. That's it. So over here we are going to use the chain rule. This is the formula of xn that I have applied here, and xn minus 1, and then I applied here the chain rule, and same story I'm doing over here. So no need to repeat again and again. So the derivative of this x minus c gives me nothing but 1. Okay, and there's no need to go so deeply here, since it's simply a preliminary of the derivatives. So we got this as f dash x, and then we are going to replace our x by c once again, and this is said to be our equation number 2. And when we replace our x by c, all these terms except this one will vanish, become 0, and now a1 is expressed as f dash c. Now we are going to differentiate this equation number 2 once again with respect to our x in order to get the second derivative. And now we just got this once after differentiation. The derivative of your a1 is 0. Derivative of your x minus c, because you see this is a constant number, so you just keep it out of the operator. So x minus c derivative is nothing but 1. So 1 gets multiplied with 2a2, it gives you 2a2 here. Okay, and then you apply the derivative at x minus c power x minus c squared, keeping 3a3 out. So it becomes 2x 2 minus 1, which is 1, and then the chain rule here, and so forth. So this gives us f double dash x like this. That's what I got, and this is my equation number 3. And then I once again replace my x with my c. So this term is going to be vanished, and all the terms right after this one will also get vanished. We are having simply 2a2 here. So this shows that our a2 is equals to f double dash c upon 2, and I replace my 2 with my 2 factorial. So you can observe that whatever the number I'm having in the subscript over here, this is coming, its factorial is coming in the denominator, and equal number of this times I'm derivating my function f of x, and I'm replacing it with my c. So if I talk about my kth term coefficient, ak, it can be expressed as 1 upon k factorial into kth derivative of my f of c. It's like this. Okay, so if I just replace all my a0, a1, a2 up to a, k, and infinity, if I replace it in my equation number 1 by all these answers, my power series can be expressed like this. Let me write down over here. So my power series f of x in terms of power series can be expressed like this. It is a0, and a0 is my f of c, plus a1 is my f dash c upon 1 factorial x minus c, plus a2, which is f double dash c upon 2 factorial x minus c whole square, plus a3 is expressed as f triple dash c upon 3 factorial x minus c whole cube, and so on. It keeps on going up to infinity. So that's how the power series is expressed, and this is what you say the Taylor's polynomial that we discussed in the while discussing the previous form. This was exactly the Taylor's polynomial. So the power series, if the Taylor series, when we say that a function can be approximated by a certain polynomial, then in terms of power series, then that power series is nothing but a Taylor series. Okay, so that's it. Now there comes a concept that if you are having a certain function f of x and it is approximated not equal to a certain Taylor series, which is this, obtained through the power series, then it means these two are approximately equal. They're not exactly equal. It means the difference of the answers of your f of c and t and c does exist. So you can say that f of c minus t and c is going to give you some error or difference value, and we just call that error as a remainder function. And this remainder function was introduced by Brook Taylor, British mathematician he was. So he expressed it. So f of c, R and C, if I just try to express this in terms of x only in general form, so my f of x is expressed to the Taylor series plus some remainder function introduced by Taylor. That's it. So this is a very important thing to be remembered and to keep in mind. Okay, so now as far as the uniqueness is understood, and the uniqueness theorem may be summarized by saying that the Taylor series of f at c is the only power series of the form I have to turn again this form. That can possibly represent f on a certain interval I. But it does not say that f is equal to the power series on I. All we really know is that if f has a power series representation at c, then that representation must be its Taylor series. That's what it means. Okay, to keep this point clear in your mind. As far as the existence thing is concerned, that what is the condition, then we can approximate a certain function by means of a Taylor polynomial. So the condition is that if you keep on increasing the number of terms, of a certain polynomial function, and the error gets minimized, means r and x will tends to 0 when your number of terms of a polynomial increases up to infinity. The error gets minimized. If this condition is getting satisfied, only in that case where we are able to approximate our function by means of the Taylor polynomial, otherwise not. Okay, so this remainder function was introduced by the Taylor, and he explains the remainder function